So if you're imagining an octahedral complex with its EG and T2G ligands, then when you're filling the metal orbitals with the number of d electrons you expect to have on the metal center, then you would fill according to the Aufbau principle. So if you had 1 electron, 2 electrons, 3 electrons, 4 electrons. Now, it turns out that sometimes we observe that instead of filling our 4th electron in the T2G orbitals, we fill it in the EG orbital. So the advantage of the what we call this high spin configuration is that we have fewer Coulombic repulsions, but the disadvantage is that we had to promote an electron to a higher energy orbital. And so sometimes we get the low spin, and sometimes we get the high spin configuration. And it all depends on the size of delta O. Now, we can get low spin and high spin configurations for D4, for D5, for D6, and for D7. And then when we get to D8 octahedral, then the T2G orbitals are completely filled and it doesn't matter anymore. And so whether or not we get high spin and low spin depends on, again, the size of delta. So we imagine that if we have a really strong field ligands that are on the carbonyl cyanide side of the spectrochemical series, if we had something like FeCN6, we might expect that it would be, that's 4 minus. So this is D6, and we observe that it is diamagnetic. So that means no unpaired electrons. And that's because with those high field ligands, the delta is large enough that it is better to have Coulombic repulsions and lots of exchange energy than it is to promote electrons to the higher level. But that's not what we see all the time. Sometimes we do see the high spin configuration. We could also see that the identity of the metal would matter. So you see high spin configurations more with the 3D metals than with the 4D or the 5D metals. And so you need to be aware as we're going along that you could have high spin or you could have low spin, and that you could sort them out with something like magnetic moment calculations.